Alright, so this is part 4 of our test on graphing rational functions. And we're going to continue with number 7 here. And just make sure you're not copying off of me. Alright, the key is if you know how to do this, do it on your own first. If you don't know how to do it, put your pencil down. I'll show you how. But then pick your pencil up and go back and do it by yourself. That's the best way to learn. Okay, let me zoom in. Let's start with horizontal asymptotes. Alright, for me that's the easiest thing to do, because horizontal asymptotes follow this formula. If the numerator degree is less than the denominator, then it's just y equals 0. If the degrees are equal, then it's y equals a over c, where a and c are the leading coefficients. And if the degree of the numerator is greater than the denominator, there is no horizontal asymptote. So that's easy to check out. The degree of the numerator is 2, the denominator 2. So like we said, since the degrees are equal, we will make our horizontal asymptote using the leading coefficients, which are 2 and 1. So it's like y equals 2 over 1, which of course is just y equals 2. So that is our horizontal asymptote. Y equals 2. Alright, make sure you put y equals, don't just put 2. And let's go ahead and graph that horizontal asymptote. And there you go. Now, you can't have a horizontal asymptote and a slant asymptote. Alright, so for slant asymptote, I'm going to put none. You know, of course, slant asymptotes happen when the top degree is higher than the bottom degree, provided that the factor doesn't cancel out. Okay, because that would just be a hole instead. Anyway, now let's talk vertical asymptotes and holes. We need a factor to see what's going on with the vertical asymptotes and the holes. So let's factor this numerator down and the denominator. The numerator is going to factor, I see that it's there's no GCF. 2x squared can only be 2x times x. 3 can only be 3 times 1. Now having said that, maybe it's 1 and 3. So there's a bit of trial and error involved. But we know that inner plus outer must equal middle. Okay, this is the middle. Inner, I have 3x. Outer, I have 2x. If I want a middle of negative 1, then I need a negative 3 and a positive 2. So here's my negative 3 right here. And putting a plus here will make positive 2 outer. Okay, I have to check one more thing though. So am I getting negative 3? Well, a negative times a positive is a negative. So we have factored it correctly. Okay, now as far as the denominator, GCF. Okay, x is common, so I'm just going to pull out that x, and that's going to leave behind x plus 1. Okay, so normally I would look at the denominator and I set each of these equal to 0, and then I would get from this one I would get x equals 0, and from this one I'm going to get x plus 1 equals 0, which, subtracting 1 from both sides, gives me x equals negative 1. Okay, so I've got these two artifacts, and normally they are vertical asymptotes, but this factor cancels out, and when a factor cancels out, it is not going to give you a vertical asymptote, it is going to give you a hole. So this one is going to give us a hole, alright, because the factor cancels out. Alright, this one is going to give us still a vertical asymptote. Okay, so let's go ahead and write down the vertical asymptote, x equals 0. Okay, so x equals 0 is a vertical asymptote, the only one. And I can go ahead and graph that vertical asymptote. X equals 0 is the y-axis. So there's my vertical asymptote. Alright, now that hole, we have a hole at x equals -1. Okay, so that means I have a hole. If the x value is -1, I still need the y value. So, to find the y value, I need to put the part of the function that did not cancel out into my calculator and see what the y value is at -1. Or, you know, I could manually put -1 in for x, same thing. But I'm going to use the calculator. So 2x minus 3 over x. Table feature. Okay, 2x minus 3 over x. So I'll hit enter. And I want to know what's going on at -1. Okay, so at -1, the y value is 5. Okay, so that means the hole is -1 comma 5. Let's go ahead and graph that. So -1 comma 5. We'll graph a hole as a nice open circle. Okay, so let's find the y-intercept next. If I want the y-intercept, then what I do is I let x equal 0. Now I have to be very careful with 0 though, because if I let x equal 0, okay, and we should probably use this version of the function right here. If I let x be 0, then that would have me putting 0 in the denominator, because x is in the denominator. Alright, so it'd be like I'd have 2 times 0 minus 3 over 0. You can't divide by 0. This is undefined. Okay, so you can't do this at all. So that means that we're not going to have a y-intercept. Okay, and that makes sense because the entire y-axis is a vertical asymptote. So of course you can't have a y-intercept. So for y-intercept, we're just going to go ahead and put none. Okay, now for the x-intercept, in general, we let y equal 0. Now when I say let y equal 0, I'm talking about f of x is like y. So if I let this equal 0, alright, in other words, the entire function has to equal 0. Well, the denominator can't be 0. So the only way for the function to equal 0 is if the numerator equals 0. So, you know, 2x squared minus x minus 3, the numerator must equal 0. Okay? Now, let's look at the form of the function after we've canceled out the x plus 1's. Okay, so the numerator would have to equal 0. So that means 2x minus 3 would equal 0. Adding 3 to both sides gives me 2x equals 3. Dividing both sides by 2 gives me x equals 3 over 2. Alright, so this is my x-intercept. And because it is the x-intercept, I will put it as the x value. Alright, and the y value is 0. Let's go ahead and graph this. 3 over 2 as a decimal is 1.5. Alright, if you didn't know that, just put it in your calculator. So we're graphing 1.5 comma 0. Okay, here's 1, here's 1.5. So here's my x-intercept. Alright, Now we need some additional points, and I'll put them on my chart. Focus on the vertical asymptote. Let's get a few points on the left and a few points on the right. So, I think I'll start over here from, for example, -3. So let's go ahead and put this function in our calculator. It doesn't really matter if you use the original function or if you use the this version after we canceled out the x plus 1s. I'll go ahead and just go back to the original function. Alright, so we hit the table feature, clear out whatever's in there. Let's go into fraction mode. So what do we have? I'll just type all this in. Okay, so it looks like this. If we hit enter, it's asking us where we want to start. I want to start at like -3. Whoops. I want to start at -3. Hit enter a few times. Alright, and we have this. So at -3, we're at +3. So that's -3, 3 would be right here. Recorded on the table as well. How about -2? At -2, we're at 7/2. Okay, that's 3.5. So -2, 3.5. So -2, 3.5. Record that on the table as well. Alright, that gives us 3 values on the left. Let's get some values on the right. So let's take a look at 1, 2, and 3, for example. At 1, we're at -1. Okay, so 1, -1. Add it to the table. At 2, we're at 1/2. Okay, so that's 2, 1/2. Add it to the table. At 3, we're at 1. So that's 3, 1. Add it to the table. So I see we need one more value at least. I always like to check out and see what's happening at 0.5 on either side of the asymptote. So I'm interested in -0.5 and +0.5. To do that, just hit the table button again, hit enter. Let's just type in 0.5. Actually, let's type in -0.5. Okay, so at -0.5, we're at 8. Okay, so -0.5, we are here at 8. Okay, so let me split this up. So at -0.5, we're at 8. Okay, at +0.5, we're at -4. So at 0.5, we're at -4. Okay, 0.5, we're at -4. Okay, so that gives me plenty of values to make a nice graph of the function. Alright, be careful about this hole. Make sure you don't just graph right through it. Leave a nice hole when you draw these branches. So your graph is going to look something like this. Okay, what's next? End behavior. On the left, what's going on? Let's see. Well, end behavior. On the left, the graph is approaching the asymptote of 2. On the right, the graph is also approaching the asymptote of 2. Okay, so as x approaches -infinity, the function approaches 2. As x approaches +infinity, the function approaches 2. Okay, we got all our points covered. Is that it? Oh, the domain. I almost forgot because at the beginning. It's weird. The domain. The domain. Got to be careful. I have these 2 branches, but the left branch is cut into 2 pieces by this discontinuity. All right, the whole. So I actually have to say the domain in 3 pieces. Now remember, the domain is strictly x values. So focus your eyes on the x-axis. So this first part of the domain goes from -infinity up to the whole, which is at -1. So from -infinity to 1 is the first part. Okay, union. Round parentheses because this is a whole. It cannot be included. Alright, it's left as a whole for a reason. It's not included in the domain. And then, x value wise, it goes from the whole to the asymptote. So that's -1 to 0. Alright, and then the final part of the domain picks up with this branch down here after the vertical asymptote. So it goes from the asymptote to positive infinity. So that's 0 to infinity. Now if you were thinking 0 to 2, you were looking at the horizontal asymptote, but this is a y value. We're talking x value, so it goes to the right forever. So that's why we're saying positive infinity. So 0 to positive infinity. Okay. And that is it for number 7. Okay, this function is a transformation of the parent function 1 over x, obviously. So we're supposed to write the equation of this function. So we just need to see how it is shifted, okay? So of course the original function would have started out centered at the origin, okay, with the y-axis being a vertical asymptote and the x-axis being a horizontal asymptote. But now it should be plain to see that we now have a horizontal asymptote here and a vertical asymptote here. I'm going to go ahead and draw those asymptotes that I mentioned. Okay, now looking to see how the asymptotes moved, alright, from their original position at 0 and 0. Alright, you can see that the horizontal asymptote moved down 4. Okay, so this graph has moved down by 4. Let me just make a note of that. Down 4 is one transformation. And it has moved to the right by 2. Okay, so we need a function that's down 4 and right 2. So we know how transformations work. If we want this function to move down 4, then we need to subtract 4 on the end, like that. Let me make this a little bit bigger for what's coming next. Okay, if we want this function to move right 2, we know that moving left and right is affected by what's being added and subtracted here inside the fraction. But it's the opposite of what you would normally think. So if I wanted to move right 2, what I actually need is a -2 in this denominator. Okay? Let's start with that and see if it matches what we have, right? If we're lucky, there won't be any vertical stretch or anything like that. So let's start with this. So let's put this in our calculator and see, we definitely have the asymptotes right. But let's see if, for example, we come up with, the point 3, comma, -3. Okay? And like right here, for example, we have the point 1, comma, -5. If these points show up in our table of values, then this is the answer. Let's put it in our calculator. So we'll hit the table button. Let me smooth this over a bit. Hit that table button and clear this mess out. Show fraction mode. I have 1 over x minus 2 and then -4. Yeah. Okay, and I want to see, for example, Do I have the point 1 comma negative 5? Do I have 3 negative 3? Alright, so hit enter. Might as well start off at the point 1. Okay, 1 comma negative 5 and 3 comma negative 3. Alright, those points are part of this function, so this must be the correct graph. Alright, so I'm just going to copy this down here. So the correct answer is in fact f of x equals 1 over x minus 2 minus 4. Okay, so that was number 8. Okay, that just only leaves the bonus. Find a decimal approximation for the x-intercepts of the following function. Remember, to find the x-intercepts, what we do is we let y equal 0. Alright, in this case, y is this whole thing. So we're setting the entire function equal to 0. But guess what? The denominator can't be 0. So the only way the function is going to equal 0 is if the numerator equals 0. So it's like we're setting x squared minus 5x minus 8 equal to 0. And we're solving this. So normally we would factor this, okay, but 8 is like 2 times 4, 1 times 8. I'm not going to get a 5. This is unfactorable. That's why they're saying decimal approximation. So we have to solve this some other way. Let's use the quadratic formula. The quadratic formula is like this. It goes, given something like this, we've got x will equal the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. To help us remember that, we used to have a song. I don't know if I can sing because I'm losing my voice. I'll try. It was like opposite of b plus or minus square root plus or minus square root b squared minus 4ac b squared minus 4ac all over 2a all over 2a. Wow, that was awful. Alright, anyway, so this is what we're using. We learned to first find the discriminant, which is this part. Okay, so let's do that right now. So we're finding the discriminant, the b squared minus 4ac part. Okay, of course a is 1, b is negative 5, and c is negative 8. Okay, so b squared minus 4ac, that's negative 5 squared minus 4 times 1 times negative 8. I'm just going to put this in the calculator. Alright, this is what it looks like in the calculator. Notice my use of parentheses. This is mandatory. If you don't use parentheses around this negative 5, you will get the wrong answer. Okay, so 57. The discriminant is 57. Okay, so that means that we've got 57 right here. So let's go ahead and do the rest of the quadratic formula. Okay, so that means x is going to equal opposite of b. So b is negative 5, so the opposite of b is positive 5 plus or minus square root. Alright, we already did this part. That's 57. All over 2a. Well, a is 1, so 2a will just be 2. Okay, so this will give us our x-intercepts. So let's turn this into decimals by putting this into the calculator twice. Once as a positive and once as a negative. Okay, so 5 plus blah blah blah. Here we go. Okay, fraction mode. So 5 plus radical 57 over 2. Enter. Alright, first it just switches these around for some reason. I don't care about that. So I'm just going to hit the toggle button to get the decimal. Okay, so I'll do 2 decimal places, the nearest hundredth. So that's 6.27. Okay, 6.27. Now I'm going to type it in again with a negative instead of a positive. Okay, now I don't really have to type the whole thing in again. If I want to take it easy on myself, I can go back to the first time I typed it in and just hit enter. Okay, now I can just arrow my way over and change this to a negative and hit enter. Okay, again it just switches it around first, but I'll just toggle it. So that gives me negative 1.27. Alright, of course I could have just typed it in again with a negative if I wanted to. But we're doing x-intercepts, so let's write this as an ordered pair. Okay, so these are x-intercepts, so these are x values. So that means I'm talking about 6.27 comma 0 and negative 1.27 comma 0. Okay, and that's it for the bonus, and that is also it for this entire test. Alright, you guys, I hope this video was helpful. If you're studying for a test of your own, you know, for my students, that would be recovery. The key is to make sure that you can do every single one of these problems by yourself. Doing it along with me just gives you a false sense of security, making you think you know what you're doing when you really don't. You don't know if you can do it until you sit down and try to do it by yourself. So make sure that you do. Alright guys, I'll see you on the next video.